Okay, so back to the eccentricities of the planets, and while you were gone, I put Uranus and Neptune in the correct order. I do know that Neptune is before Pluto. I was distracted by Pluto. And so first completely left them out, and then when I did write them down, I put them in the wrong order. So what we were saying, just as the video ended, is that Neptune has, so Pluto has the biggest eccentricity, and then Mercury. On the other end, Venus has the smallest eccentricity, and then Neptune. Neptune's is 0097. Now, then there are no units on eccentricity, right? Because it's a length over a length, which the units are going to cancel. If you think about the fact that Pluto's orbit then is the flattest, and Neptune's is one of the most circular, it might help to explain for you why Neptune, there is a point in Neptune's orbit where Pluto moves inside of it. And I think you probably would have learned that somewhere in your earlier life. And no, they'll never collide. Like, these are zillions of kilometers and three-dimensional, so you never have to worry about a collision happening here. You'd probably win the lotto about 8 times before that would happen. Okay, but it's because of the difference in the eccentricities. The Earth is actually the third least eccentric. The Earth's eccentricity is 0.0167. So we're moving in ellipses, but like Venus, Neptune's, Earth's, like that's awfully close to a circle. Even the most eccentric isn't very far away. Okay? So that's the first law. Kepler's second law says that as the planet then moves around the sun, with the sun in an ellipse, with the sun at one of the two focal points, and I've way over exaggerated the flatness here, but I'm just doing it so we can see the second law. So the second law says that as the planet moves around this sun, if you were to stand here and time out a certain amount of time, you could find an area that the line between the sun and the planet, the area that the line would sweep out. And then if you let the planet get to the point where it's like the furthest away from the sun because of the eccentricity, and you were to time it for the same amount of time and find the area swept out in that time, if delta T1 is equal to delta T2, if the time periods are the same, then the areas will be the same. So really what it's saying is that the planet picks up speed when it's closer to the sun because it has a bigger distance to travel. And it slows down when it's further from the sun. Okay, and it has to do, we know it does that by if these two areas are the same, then it must be going faster here than it is here. The point closest to the sun is called the perihelion. And the point furthest from the sun is called the aphelion. Okay? Lots of people think we are the furthest from the sun in our winter. But remember, our Earth is tilted, and when it's winter for us, it's summer in the southern hemisphere, and we can't be further from the sun in the north on one day and on a different day for the south, right? The distance we are from the sun has no effect on our seasons. Our seasons are caused by the tilt of the Earth. And what causes the effect that the distance we are from the sun has no effect even on our temperature. Because, remember, our eccentricity is only 0.0167. So even though I've magnified it so it looks like the distance on the right-hand side is a lot bigger than the distance on the left, it's not really true. And in actual fact, the two focal points for our ellipse are both inside the sun. One is the center and the other is closer to the edge. So there's really not a big difference in the distance from one side to the other. But it is why when you use that chart on page 955, it says the average or the mean radius of orbit because it averages these two sides. So when are we closest to the sun? We are furthest from the sun on July 4th. And we are closest to the sun on January 3rd. Okay, so when I taught in the States, I used to tell my students there, look, even the sun moves away on your holiday in July. Okay, apihelon means away. A goes with away. Perihelon is the when it's closest. July 4th, January 3rd, not connected to the seasons. Okay, what causes the seasons is the tilt of the Earth and the sun's direct rays hitting either in the northern hemisphere when we're tilted in or in the southern hemisphere when we're tilted away. This for us would be summer, and we're up here. This for us would be winter. And when it hits right on the equator, that's spring and fall. Not connected to Kepler's laws. So Kepler's second law, I didn't write the words down, but it says a line drawn from the sun to the planet sweeps out equal areas in equal periods of time. Okay? Kepler's third law is actually the one that gives us the equations. The third law says the average radius of the planet's orbit cubed, the average radius, because remember it's going to be different depending on where it is, the average radius of the planet's orbit, and that's an R, and we'll do R for planet. Like so, if it's Jupiter, we'd put a J there, E for Earth. So the average radius of the planet's orbit cubed over the planet's period of revolution. Revolution is when one object is moving around the other. Rotation is when it's spinning on its axis. So the planet's period of revolution means how long it takes to go around the sun. Period is a capital T. We'll put a P for planet. Squared is equal to a constant for all objects orbiting the same central body. So the equation then is R of the planet cubed over T of the planet squared is equal to a constant.